Now, more functionality in cars will give hackers more scope to attack vehicles, and threats will increase with the move to autonomous vehicles. So here, to offer some solutions in a presentation titled Cost-Effective Hardware-Based In-Vehicle Network Security is Todd Slack from the Secure Products Group at Microchip Technology. Todd, it's all yours.
Thanks for the introduction, Nick. Your intro into the presentation has summed it up nicely, so I think we can just get right into it. There's a lot going on in the automotive world as it relates to security. So there is no shortage of events going on in the automotive world in terms of security breaches. We have seen a number of OEMs around virtually all regions impacted to some degree by vehicles that have been hacked. The result is that we are seeing more and more cybersecurity specifications coming out of the likes of ISO and SAE. We see a major change coming within the industry as we move from CAN 2.0 to CAN FD, which I'll talk about as well during the presentation. And with all of the vehicles being connected now, the attack surface continues to grow. Ultimately, we are seeing OEM cybersecurity specifications coming out as a result of all of the security breaches. And basically, many of these OEMs are participating, as with tier ones and silicon providers, in a number of consortiums or standards bodies like ISO. This is just a subset of the many specifications that are out there. There are many global recommendations coming from ISO and SAE focused on security. Here we show a mix of some security organizations and some focus on functional safety. We are focused on security, but we find the two intermingled quite a bit. As we look to those specifications, really OEMs are pulling out three major components as requirements in their own OEM cybersecurity specifications. So there is a need for secure key storage, which requires a hardware secure element. There is then first priority in the upgrade to the specifications to support secure boot at each of the ECU nodes. After secure boot, there's oftentimes a tie-in to secure firmware update to make sure that the firmware running on your host controller is trusted. And then after you have verified that the boot process is trusted and the code is trusted, then we would move to message authentication. In many cases here, we're talking about ECU to ECU authentication, and we'll talk about message authentication through CMAC, which is an AES-based process. So what are the tier ones to do? There are so many OEMs pushing out new cybersecurity specifications. Many tier ones don't have the history of cybersecurity expertise within their organizations. So they are faced with a challenge to upgrade some of their long-standing ECUs that may have been based on a host MCU or MPU that had no security. And in order to upgrade, their investigation often drifts into looking at upgrading their host microcontrollers. In most cases, we're looking at an on-die dual-core HSM sort of solution. The focus within the Secure Products Group, which I'm a part of within Microchip, is really for companion solutions, which we are seeing a lot more traction for in the marketplace. And the idea there is that we can minimize the impact to your existing architecture, your existing solutions, and simply add on a secure element to take on the cryptographic heavy lifting and support the key storage requirements, secure boot, and message authentication. So while I mentioned on an earlier slide that there's a lot of focus on CAN 2.0 to CAN FD, we also see other mediums like in the EV space transmitting message authentication across RF. So as we explore the attributes of automotive secure elements, I've mentioned secure key storage as a main component. The reason for that is if we do tie into CAN communication that involves authentication, you do have to securely protect your AES keys, among others. Ease of integration is important in time to market. So if you have less impact on your existing application code and can bolt on a secure element, then you can get to market faster. It's important to have public key agreement schemes in place so that each of the ECUs in the vehicle can cryptographically come up with the same key. There are a number of methods to do that, like ECDH, ECBD, or simply having a gateway generate keys and encrypt them for each individual ECU so that those keys are never exposed on the bus. And then performance is important as well. So adding cryptographic acceleration in hardware is important so that you have minimized the impact on your boot time within the vehicle. And then as we look at automotive grade requirements in ACQ100, automotive grade 1 is a good target as we see that it fits most of the functional safety and security application nodes that have to be upgraded. So one first thing to note when discussing hardware-based security is to compare it to software, basically. Software cannot protect keys, and that includes standard devices or standard microcontrollers that do not have protections against side channel attacks. So some simple ones here show an image of a microprobe attack where you can drop down on the top surface of the device. And on this slide, if you look at the lower right, titled Standard Devices, that would be a microscope shot of the top surface of those devices where you could drop microprobes down on data lines or test probe points and extract key information or monitor the use of a key, which also allows you to eventually extract the key. So having a multitude of side channel attack mitigation techniques in place on your hardware-based secure element is important. It should start with an active shield. You should have protections against differential power analysis. Some of those tie into randomized math operations, environmental tampers to detect when the device is being put into an out of specification sort of state, typically using lowered voltage and lowered temperature to get the device to misbehave. And ultimately, we have reduced testability by design in dedicated secure elements. And therefore, you can maintain the testability that you expect within your host microcontroller. However, since testability and security are in opposition to each other, then you can keep your keys in a device that has reduced outside testability. So here's a look at a crypto automotive security IC, which is the trust anchor, a secure element inside an ECU, a very high-level view where you would basically attach the TA100 or some other secure element to your existing processor. Typically, that would be done through a SPI connection for throughput performance, but there are also variants and other host controllers that need I2C, and so those are also available in the market. And in this case, you can upgrade to HSM status with an external solution. And so you can meet the OEM cybersecurity specifications with little disruption to your existing design. That also includes a little disruption to your application code and potential existing ASIL ratings from a functional safety point of view. There are a number of different algorithms that OEMs are requiring through RSA, ECC. CMAC, as I mentioned, is common in the message authentication world for CAN. And it all comes down to the quality of your keys. And those keys should be based upon a globally recognized RNG implementation or random number generator. And so it's important to be based on something like the latest and greatest SP800-90. Use cases, I've already mentioned secure boot, high priority message authentication, high priority hardened TLS. The ability to add on quite simply is important. We see wireless charging entering the automotive space, and secure elements are required in that arena. And then we also see EV battery management systems and battery modules having to authenticate themselves. Smaller form factor packages are coming from a multitude of secure elements out there. As you look at some of the smaller form factor ECUs, for example, like a refit. Whoops, I gotta go back. Secure elements are also routinely offering smaller form factor packages, as we see some ECUs with real estate constraints. For example, on a rear-facing camera, you may have a PCB that is only 1 inch by 1 inch, so the smaller the form factor, the better. Secure boot has its challenges depending on the individual ECU boot up time requirement. In some cases, they're required to start communicating on a bus within 100, 150 milliseconds, and so you may or may not have time to verify 100% of your code. So a flexible secure element is important, where you may find yourself in a situation to partition your code, where you verify a certain percentage of your code before that 100 or 150 milliseconds, and then allow communication on the bus if that code looks trustworthy. And then in the background, after communicating on the bus, you would still, with good crypto hygiene, continue to verify the remaining code. As we talk about CAN-FD and CAN Message Authentication, AutoZAR has focused on coming up with a common frame format. So typically we're looking at an 8-byte payload for the message. There is a sequence counter. Some documents call that a freshness value, which is included in the MAC or the CMAC to prevent any replay attacks. And then we are traditionally seeing a 16-byte MAC. In other worlds, like Jaspar, where there is a desire to continue to support CAN 2.0, this is configurable, and so you can configure your MAC all the way down to a truncated 1 byte and reduce the size of your sequence counter to even fit in an 8-byte payload. Certificate chains can be a complication for Tier 1s, as they may not have had a history of supporting X509 type certificates. So as you look for secure elements, it is nice to be able to find something that may be pre-provisioned. Ultimately, it would be routed back to an OEM root certificate that would be provided during the engineering phase of development. Likewise, the intermediate certificate, typically associated with a Tier 1, would be created during engineering development. Those would be static certificates written into a secure element like the TA100. And then as the TA100 creates internally its own unique private-public key pair, then it can be signed with a unique platform certificate, most associated with an ECU unique certificate. So security considerations at every node. I mentioned on an earlier slide all of the focus on new specifications, new best practices. And here we look at SAE J3061 as an example, which is now being folded into ISO 21434. Basically says that if you're building any node within a vehicle that is networked, that thou shalt perform some risk assessment to determine how a hacker might infiltrate the node, and then some sort of attack tree analysis to determine what bad things could happen if they do. During that investigation, during that risk analysis, we typically see Tier 1s discover, if they didn't already know, that the only way to justify the security implementation in an in-vehicle networked node is to have hardware-backed security with secure key storage. And so, just a recap of the 3 pillars for automotive security, the very common requirements that we are seeing coming from most OEMs builds upon secure key storage, then secure boot, over-the-air updates for secure firmware updates, typically a signed event and a signature verification, and message authentication across multiple mediums, whether it be BLE, Bluetooth, RF, or CAN. And if we think about how you can integrate secure elements into your solutions, it's important to think about scalability. If you take the time to integrate a secure element into one of your nodes, it should be simple then to adapt it into other nodes that you may be building. Interoperability is extremely important. There will be different silicon solutions in different nodes, and so it's important that OEMs choose public key infrastructure, public algorithms, so that those different devices can interoperate. Maintain performance. I talked about hardware crypto acceleration. If you start to add software capabilities for required algorithms within your host microcontroller, you will typically not meet the OEM cybersecurity performance recommendations, and so that can be accomplished with hardware acceleration and secure element. And then hardware protection is extremely important. As we go back to the center of all of your security comes down to how well you protect your keys, and so you should evaluate your secure elements accordingly. Ecosystem provisioning can be a complication, so something that a Tier 1 should investigate early on in their selection process. And then the option to preserve legacy allows you to upgrade your individual nodes without a full re-architect of your design. And then there needs to be, in some cases, some backwards compatibility. So I appreciate your time today in this presentation about some of the challenges faced in the automotive industry by new cybersecurity specifications and some solutions where a secure element may reduce the complexity, time to market, and cost to upgrade your solutions.